Curves are best fit in Algebra 2. Linear regression, quadratic regression, cubic regression, exponential regression. These are all different types of regression lines that you will use to determine the best fit curve, and you'll find them all in the same place, and it's based on a whole lot of things, and we're going to talk about what you're going to look for. All right, let's get going. All right, so in the calculator, the first thing you're going to want to do is put your data in your calculator. And I'm going to go ahead and get started with this because we're going to have a couple of processes we have to do. When we go to Stat, Edit, let me go back and show you Stat, Edit, you put your data in L1 and L2. And I'm going to go ahead and start putting some data in because it'll save us a little time. You just go ahead and make sure you hit Enter. Okay. And also, something else that you're going to want to do is you're going to need to turn on a couple things on your calculator. When you're doing statistics, some of the things you want to have on all the time, some of the things you don't want to have on all the time. 1, 2, 3, 4, 6, 8. All right, because it will drive you crazy when you're trying to graph other things. One of the things is stat plot. Okay, you only want to do that when you are actually using the statistics part of any kind of test, because it'll aggravate you to no end because you won't be able to figure out what's going on because you got all these little blocks popping up on your screen. So only turn the stat plot on when you are going to do the statistics parts of your test. Okay? All right, so once you get your data put in, then you want to turn your stat plot on. If you're doing the statistics part, you go to second y equals, and you roll over here to number 1, and you roll over to on. Make sure it highlights on. Why is it not moving? And hit enter. Okay, and now it is on. Something else you want to do, now this stat plot part is the part that I'm talking about where you don't want to leave it on all the time. But there's another thing that you can turn on at the beginning of any test, and that's called diagnostics. And you go to second catalog, and you roll down, it's in our alphabetical order, to the D's. And you're going to want to turn the diagnostic on. Okay, diagnostic on. You hit enter, and hit enter again. When it says done, it is now on. You can put that on at the very beginning of the test and leave it on for the entire test. It won't mess things up. It is important when you're doing statistics because it gives you an R value that will not show up unless you have it turned on. Alright, so once you've got your stat plot on and you've got your data in, you want to hit zoom 9 so that you can see your little blocks. Okay? If you see little blocks on your screen and you don't want to see little blocks on your screen, you know that it's the stat plot that's on, you need to turn it off. All right, so then you're going to determine which regression line that your data fits best, whether it's linear, quadratic, exponential, cubic, quartic, whatever. Okay, once you do that, then you'll hit stat, calc, and you'll hit that regression line. And then once you have that, you will determine how to go from there. You want to make sure that you pick a line that will fit most of the data. Okay, so when you graph it, and we'll show you in a few minutes how to do it, you'll go to y equals and make sure that your cursor's on the right hand side of the equal sign. You'll push bars number 5, which is statistics, up across the top EQ, number 1, and enter, and I think enter one more time. And it'll put that line in. So let's talk about it as we're doing it. All right, first we need to talk about is the n+1 point principle. And that states that for any set of n+1 points in a coordinate plane that pass a vertical line test, there's a unique polynomial of a degree at most n that fits the points perfectly. What that means sounds like Greek, but what that means is this. Think about it. In order to graph a line, you need to have at least 2 points to graph it, okay? And we know that a line is in the shape of y is equal to something like x plus 2, where that is a degree of 1. But you need 2 points in order to graph it. So a degree of 1 needs 2 points. to graph a parabola, which would be something like y is equal to x squared plus 5x plus 4, where it has a degree of 2, you need 3 points. Otherwise, it could be just a line. Okay, you need to have that third point to show possible curving of a line. All right, so what the n plus 1 principle means is that for every degree polynomial, you want to try a regression line of 1 degree higher so that you can possibly have all the points to fit in on that graph. Okay, so if I wanted, say I had 4 points given to me in some data, I would try to see if a quintic would work if it had 4 points. If I had 3 points, I would try a quadratic. So it's always 1 degree higher for the regression line, depending on how many number of points they give you in your data set. Now, once they get to 6 points, pretty much it's going to be always cubic or quadratic. You don't have anything else outside of that. So once you get to that, just know it's probably going to be cubic or quadratic. And start there. The best way to tell is look at the scatter plot of the points. So once you get it all in, then you hit zoom 9. What do the scatter plot points look like? Are they curving? Are they straight line? What are they doing? Try to figure out, a general idea. Then check the equation. If you have your diagnostic on, you'll see that r squared. Let me bring it up. I'm going to do stat, calc, and I'm going to pick something that's wrong and hit enter. Okay, you'll have an r squared value right here. All right, that r squared, you want to have r squared as close to 1 or negative 1 as possible. That would mean that it's a very, very strong correlation. Well, 0.7 is not super strong because it's not that close to 1. So I would know that this one would probably not be a good fit. Okay, looking for that is another way to tell which one would be the best one to pick. All of these are things you need to consider when you're picking the regression line. Okay? All right, so let's take an example of cheese consumption in the United States. The table shows the average annual consumption of cheese per person in the United States for selected years from 1910 to 2001. Now, when you're putting years or years into your table, I use 10, 40, 70, 75, 95, and 101 because this is very, very huge numbers. It's very hard to get into your graph, and it's going to make your graph difficult to look at. So when you're working with years, you can start with that because it's 10 years from 1900, whereas 2001 would be 101 years from 1900. So when we're working these problems with years, I'm going to use 80, 100, and 112 for the 3 years we're going to be looking at in just a second. All right, I have 1, 2, 3, 4, 5, 6 data points. When I've already happened to put these, when we were talking earlier, into my calculator. So I went to stat, and I put all that in there, and then I hit zoom 9. And there's my data set. So I know it's curving. All right, so I'm going to pick cubic because I have 6. I'm just going to try that first. Let me go look and see what it says. Stat, calc, and cubic is number 6. So hit 6, hit enter. And it has an r squared value of 0.997. That's pretty good. So I'm going to look at this. Now, be very, very, very careful. I did this earlier and messed up because I was going too fast. Once you get up into cubics and beyond, you have to be very, very careful because you see this little sneaky little e right there? That means times 10 to the negative 5. So really what that means is that it is 5 places to the left from the decimal. So instead of putting in 9.24, you would really write 0.123400924 x cubed. Be very careful with these because that little E is hard, it's easy to miss, okay, so just look very carefully. And then the B would be negative 0.01, C would be 0.31, and then D would be 1.80. So this would be 1.4. Okay, so I have my equation line, and I'm going to go right here and write down my equation line before we get going too far. So I'm going to write y is equal to 0.1234924x cubed minus 0.01x squared plus 0.31x plus 1.80. If not, when you put this stuff in, you're going to get a number way, way, way off from what you got here. So go back if that happens and check to see if there was a hidden little E in there and fix your decimals, okay? So this is our equation of best fit. Now, let me go back to my calculator. All right, so I want to look, got my graph and I got my points, but I need that line to go in there. I'm going to go to y equals, I'm going to have my cursor to the right of the equal sign, and then I'm going to go vars, number 5 statistics, scroll over to EQ, which is equation, and hit enter. And it puts it in there for me, and you notice there's that E to the negative 5 in there. There was no other E's, everything's good to go. And I graph it. And it should draw the line right through my scatter plot points. And when it does, you can tell that all the data fall on that line very, very nicely, and you can tell it has that S kind of curve thing going on. All right, so we know we picked the right one. All right, so then I need to predict, I need to predict what the consumption would be in 1980, 2000, and 2012. Well, again, I'm going to use 80 for 1980, and that's going to go in where the x's are in this equation. So when I do that, put my calculator and go to second quit, clear all that off. I'm going to type 0.1234924 parenthesis, and I'm going to put my 80. I'll put another parenthesis, and that's going to be cubed, raised to the third. Then I'm going to have minus 0.01 and the parenthesis 80 squared plus 0.31 parenthesis 80 and plus 1.8. Okay, and hit enter. All right, and that's going to say 9.9. Okay, they're saying 9.9. All right, I'll put 9.9. All right, for 1980. All right, so then I'm going to do the same thing for 2000. So I'm going to go back to my equation. Remember, I told you hit second enter, sorry, and go back and change anything you want to without typing all that mess. Now, because I have 3 digits I want to put in, I'm going to hit second insert, and I'm going to have 10. Oops. Okay, 100. So I do the same thing for the next one. Second insert, and put a 1, and change that to an O. Delete that. Go over to the last one. Second insert, and put a 1. Delete that one, put O. Oh. Oops. I'm going to have to finish that one. Plus 1.8. Okay. Hit enter, and that's saying about 25.2 for 2000. So I'm going to write 25.2 for 2000. And then 2012, I'm going to use 112. So I'm going to go back. and then hit second enter and go back. Oops, and go change that to a 1 and a 2. 1, 2. 1, 2, and hit enter. And they're saying about 40.9. Alright, so 40.9. Okay, so approximately 9.9 in 1980, 25.2 in 2000, 40.9 in 2012. Now, the problem with estimating, the best estimates are between the years that you have your data. In other words, between 1910 and 2001, if you have a year between those years, that is going to be a pretty good estimate, okay, because that's within your statistics that's been given and that have been documented. Okay, that's called interpolation. That's data that falls within the statistics that you're given. Those you can count on pretty confidently to be true. However, 2012 is not within our data that we've been given, and it's not as likely to be true. So it's called extrapolation, data outside the statistics given. It can give you an estimate only if it's outside the data given, the data or the years or whatever. You can't have as much confidence in it because lots of things could happen. You could have suddenly, that would be, all we had in the world to eat was cheese for some strange reason. Or you could have suddenly all the cows that produce cheese got some kind of illness and died, so then no one was eating cheese. Or it was somehow tainted, different things. So anything outside of this range of data is just an estimate. I'm not very confident. I wouldn't bank money on it, in other words. So that would be, 2012 would be an extrapolation, and that would be the year that I would have my least confidence in. We did a statistics in another class, and we were talking about cases of mumps, and as the years gone by, the cases of mumps have gone down because of vaccines. Well, if you were to predict what would happen in, a future date, like say 2030, okay, they would say that the cases of mumps was like a negative number. Well, you can't have that. And then something else could happen. You never know what could happen that far ahead. So whenever you're doing this, make sure that you're using statistics within this range, or don't be super confident in your answers, okay? All right, so I think that was the last of this slide. Yes. If you have any questions when we're working on this, all of these are going to be very, very similar. There's no difference between exponential and quartic or any of that stuff. You're just looking to see how many data points you have and trying to predict. Put your points on there with your scatter plot, look the shape, look the R squared kind of thing, and then make an estimate on which one should be used. Okay? And we're going to practice this in class. So if you have any questions, just come see me.